Now remember, I've already said this in the waves portion, but remember that the medium itself, whatever the wave is moving through, determines the wave speed, and that's all. There's nothing else that determines the speed of that wave. I can change the speed of the wave, but there's only one way to change it, and that's by changing the medium. Either you can change what the medium is, I can change what that material is, or I can change something about the medium. For instance, I might change the temperature of the air. So this equation that I taught you in waves, this V equals F lambda equation, that wave equation is true. Speed does equal frequency times wavelength. However, the speed doesn't depend on frequency and wavelength. The speed depends on the medium. And if that medium doesn't change, neither does the speed. And I'll illustrate that in a second. If the medium doesn't change, the speed can't change. And if that's the case, what that means is that the frequency and wavelength are going to be inversely related to each other. Frequency increases, wavelength decreases. I'll show you what that means and how that works out. So let's say you have a guitar, right? The idea behind a guitar is to make music that sounds good. So if you play a guitar, you're going to get 6 different frequencies, in case you didn't know, because it has 6 strings. The lower frequencies are the thicker strings. In this case, they're on the top of this guitar. And the higher frequencies are the thinner strings. They're at the bottom of this guitar. And so ideally, what you want to happen is you strum that guitar and you want all of those frequencies to reach the hearer's ears at the same time, right? Because that's the way it's supposed to work out. So you have all 6 of these different frequencies. They hit your ear at the same time because this equation governs this. V equals F lambda applies here. So we just learned that the speed of sound is 340 meters per second, all right? So someone might think, okay, we have a 262 hertz frequency being played. Let's say that's the blue one. What happens if I increase the frequency to 330 hertz? Let's say it's the red one, right? So if we only think about math, what we might now think to do is I've increased this number from 262 to 330, and now I might multiply 330 by 1.3 to get a new speed, and I get 429. Is that the new speed? Did the speed of the sound change? Is it 429? Did I change the speed of the sound by changing the frequency? No, I didn't. We can't do this. This is not right. Because remember, it's only the medium that changes the speed of the sound. If this was the case, let me tell you what would happen. If changing the frequency changed the speed, that would mean that the higher the frequency is, the higher the speed is, which would mean that the higher frequencies would reach your ear first. All of these notes would travel at different speeds. I'll illustrate that again. Here it goes. You would strum your guitar, and the high frequencies get there first, followed by the lower frequencies. That means if frequency changed the speed, all the notes would reach your ear at different times, which would mean the music would suck. Your ear wouldn't be able to make sense of it. So this wouldn't happen. This can't happen. I want you to understand this is not the case. Changing the frequency does not change the speed. What actually occurs is that if the medium doesn't change, the speed doesn't change either. So this 340, as long as I'm playing my guitar in air and the air is remaining at a constant temperature, that 340 stays the same. It doesn't change. So what actually occurs when I increase the frequency to 330 is that the wavelength is going to simultaneously decrease so that this speed can stay the same. And in this case, it'll decrease from 1.3 to about 1.03. That's what the wavelength would have to be. And this brings about this great illustration that we're going to refer to later on, which is that this is a wave that's obviously of higher frequency. There's more waves per second occurring here. Lower frequency wave on the bottom. Well, the higher frequency wave has a shorter wavelength, whereas the low frequency wave has a longer or higher wavelength. And so frequency and wavelength, as I said a minute ago, are inversely related. Now, this is what happens if the medium doesn't change. However, if we do have a medium change, the speed will change. Medium changes do cause speed changes, and we can change the medium by either changing what the medium is, and I'll get to that in a minute, but I can also just change something about the medium, like the temperature. If I change the temperature, I can change the speed. And as far as air is concerned, as the temperature of air increases, so does the velocity. Same thing with the density. As the density of air or whatever medium I'm talking about increases, so does the velocity. All right? Because remember, it's the particles of that medium that are propagating the wave. So, sound wave, if we're talking about different media, sound going through, in this case, we have air and water and steel. Sound is going to travel faster through more dense media. Now, I want you to watch this because it happens fast. There's going to be a sound wave propagating through these materials. It's going to happen fastest in the steel. Watch. All right, it already happened. Watch. The steel happens so fast. I'll start it again. The steel is done, then the water, and then we still have this sound wave propagating through air. Now, this is drastically exaggerated, but the point here is to illustrate that sound going through air is actually pretty slow. As far as sound is concerned, you almost can't get slower than sound in air. Here's a table of speeds of sound in different materials. In water, now remember, in air, we're talking about 340 to 350-ish, depending on the temperature, meters per second. In water, 1,433 meters per second. In iron, 5,130 meters per second. Steel is 6,100. And a diamond, 12,000 meters per second. So these are very, very dense materials. Sound travels much faster through dense materials. But remember, the temperature of the medium also affects the speed. At 0 degrees Celsius, we actually go down to 330 meters per second. And I've already told you 20 degrees Celsius, around 340, 343, depending on what publication you look at. 343 meters per second. So the higher the temperature, the higher the speed, right? So again, we're just talking about how if we do change the medium, either change what the medium is or change something about the medium like the temperature, then I can change the speed of the sound. Now, as a comparison point, when we get to light, the speed of light, we thought diamond was fast. The speed of light is 300 million meters per second, which is why I told you before, when you see that lightning, that light wave is reaching your eyes almost instantaneously. Not quite, it does have a speed, but it is almost instantaneous.